Okay. Welcome to today's colloquium. We're very fortunate to have Javier Garcia here today. Javier is an expert on actually on laboratory astrophysics, computational atomic physics relevant to X-ray astronomy, and interpreting X-ray sources. He got his bachelor's degree at La Universidad de Zulia in Venezuela, and his master's degree at the Venezuelan Institute of Scientific Research. Then moved to Catholic University near Washington for his PhD, where he worked at Goddard Space Flight Center with Tim Coleman, and that's the first of his many associations with CU and Gilla, because Tim Coleman was a graduate student of Dick McCrae's here. He had postdoctoral positions at Western Michigan in Kalamazoo and the University of Maryland, working with Chris Reynolds in 2011 2012. He then moved to the Harvard Smithsonian Center for Astrophysics, where he was a postdoc with Jeff McClintock from 2012 to 2016. And in 2016, he moved to Caltech as a postdoc and concurrently had a von Humboldt senior fellowship with Jörn Wilms at Bamberg in Germany. And so that is two more associations with Gilla, because Chris Reynolds, of course, was a senior research associate here before moving to Maryland, and Jörn Wilms was actually a graduate student under a Fulbright for a year with me. So I didn't know that actually until last week. I worked with Jörn. Since 2019, Javier has been a research assistant professor at Caltech, where he is a member of the New Star team, and he is the winner of the 2021 American Astronomical Society Laboratory Astrophysics Division Early Career Award. So two Early Career Award winners in a row. They already won the Dynamical Division similar award. Javier uses his insights into X-ray, the behavior of X-ray transitions in various atoms and ions to study the heating and reflection of X-rays off accretion disks, and is an expert on the reverberation mapping of accretion disks. And today, he's going to tell us how we can use these methods to probe the space-time near accreting black holes. Javier.
On Zoom, can enter stuff in the chat.
Sorry, yes, if you are on Zoom and have any questions, please type them into chat. We're monitoring the chat, and we will pull those questions in at the end.
Okay, and it's okay for me to remove the mask now, right?
Yes.
Okay. Well, thank you so much, Mitch, for such a nice introduction. You actually make me sound better than what I am. I'm very excited to be here. This is the first time I give a public talk in person, so I'm divided between excitement and fear and confusion. There is no Zoom window in front of me, so that's weird. But yeah, what I want to do today is, of course, give you an overview of a lot of the research that I've been doing, as Mitch say, on accreting black holes. This is not necessarily working, right? There you go. And as anybody else today in science, nothing is done alone. I'm very lucky to have a lot of collaborators and interacted with the students and postdocs. People normally will say they have the best student and the best postdocs and the best collaborators in the world. They're lying to you. That's not true. I have the best ones. They're here. They're really great people, and a lot of the results I'm going to show today belong to them, so they have the credit. This is the outline of the talk. I will give a very brief introduction on why black holes are important, in my opinion, and why do we look in X-rays for them, and specifically why we concentrate so much in this iron line that I will mention a lot through my talk. This has a lot to do with the estimation of the spin of the black hole. This is the important point, and I will explain why. And it's all based on a technique called X-ray reflection spectroscopy that I have worked for many years now. We're now moving to adding timing, the time domain into these models. So I'll also show new results on that kind of modeling. And then if I have time, a couple of slides on current and future developments. See if this will work. Great. So X-ray astronomy is actually much newer than many other wave bands in astronomy. It started in the 60s when Riccardo Giacconi started doing the first observations of astronomical sources with X-ray detectors. This is, of course, because the Earth's atmosphere is opaque to X-ray, so we have to go to high altitudes to put detectors at high altitude to be able to observe sources. There is a really interesting story in one of Keith Thorne's books about how Riccardo used rockets to put essentially like a Geiger counter in a rocket to do the X-ray observations. And a lot of the funding apparently came from the Department of Defense, because he convinced them that you could use this as a mechanism to spy on the Russians. You have to think about the Cold War, in the middle of the Cold War, and say, well, if they're doing bomb tests or somewhere, we could potentially see that if we look into X-rays and gamma rays. So I thought, if it is true, it's a really clever idea. The first observations were looking at the moon to see the X-rays from the suns reflected at the moon. At that time, there was only known X-rays from space were coming from the sun. And what they actually found was a much brighter source coming from the constellation of Scorpio, that's known today as ESCO X1, and it's an accreting neutron star. But you know, it's not a black hole, but it's a compact object, and from there, essentially, X-ray astronomy was born. I will skip a lot of the history. I'll jump back to the 90s, where the first CCD detectors, this is charge coupling devices, kind of like what you have on the camera of your phone, start flying, obviously sensitive in X-rays. And there were many developments very quickly. Lots of X-ray sources were discovered. Many of them were immediately associated with galaxies. And that's how the association of the active galactic nuclei to a lot of X-ray emission was done. And the idea of supermassive black holes in the center of galaxies was already around. So a lot of the spectra start showing evidence for a lot of iron present in where the X-rays were emitted. So one of the most emblematic works is what I'm showing here on the bottom, where you see this is the region where iron K lines are produced. These are inner shell transitions. The rest frame energy is 6.4 keV, and you can see early observation done with a telescope called ASCA of a Seyfert galaxy, MCG minus 63015, and a ratio plot. When you remove the continuum, you see this excess that shows clearly emission of iron. The importance of this particular detection was the fact that the emission is not symmetric, as you would expect from a normal emission atomic line. It's very, very asymmetric and skewed towards low energies. And this was quickly identified as, or explained as, the emission occurring near a supermassive black hole and affected by gravitational effects, relativistic effects. So it was a Nature paper led by Tanak et al. And the explanation for this is roughly like this. If you think about a line being emitted in something like a disk that is rotating at great speeds, you will tend to see something like in the upper panel, you'll see a double horn caused by just Newtonian going away and towards you, and then you have this split of the emission line. If this happens close to a strong gravitational field, what happens is that special relativity will add a beaming effect. It will act as a magnifying glass for the radiation that is coming towards you, and demagnifying for the radiation that goes away from you. So you have an asymmetric profile, meaning the blue side of the line gets the intensity increases while the red one decreases. And on top of all that, general relativity will add a gravitational redshift to the entire profile. So if you put all these things together, you get to see this skew and asymmetric profile, broadened line, very resembling what I showed before. And this, of course, will depend to some extent on the properties of the black hole. Here I'm showing two different line profiles. If you're referring to a Schwarzschild black hole, what it really means is you're using the Schwarzschild metric to describe the space-time. and that's a black hole that has no rotation. In the case of if you use the Kerr metric, in that case, you allow for having angular momentum in the black hole, sorry, and that will cause even more distortion. And the reason for this, sorry, is because it will depend on how close emission occurs to the black hole. The closer to the black hole, the more it feels those gravitational effects, the larger is the distortion in the spectrum. And this has to do with the spin, because if you have a material forming an accretion disk around the compact object, what happens is that disk cannot go all the way to the horizon. It will actually have a sharp, we believe it has a sharp edge, that we call the inner radius. And the location of that, the radius at which that happens, is the radius of the last circular orbit that are stable. For any radii smaller than that, what you have is material directly plunging to the black hole. So in order to have a proper accretion disk producing these sort of lines, you have a particular edge that sits at a particular radius. The acronym is ISCO, so the ISCO radius, and I'll refer to it from now on as the ISCO radius. So the radius of the ISCO will depend on the spin. The faster the black hole spins, the closer it allows for circular orbits. These are just properties of the general relativistic effects, right? So that means that if we can model this distortion accurately, then you have immediately access to an estimate for the black hole spin, which is a very important quantity. Black holes, in a way, are extremely simple objects in the universe. In astrophysics, they're described only by mass and spin. So if you can measure the spin, you're halfway through to describing them. And this is the kind of things that we're seeing now even better with modern satellites like NuSTAR. NuSTAR is the first focusing hard X-rays telescope. This is the one that is managed at Caltech. The PI is Professor Fiona Harrison. And this is just an example of one of the earlier observations of another galaxy, Mercurian 335, where we obviously see the clear effects of the distortion due to the supermassive black hole. The blue line is the same model taking away all these effects, right? So you'll see that the blue model will never be able to reproduce the data. And traditionally in this field, people talk a lot about the iron line and the iron line method, and how the iron line is what we use to measure these things. But I just want to emphasize that is really, nowadays, is really the entire reflection profile. And this is what we spend a lot of time trying to produce in an accurate way. One of the cool things of this technique is applicable to a wide range of compact objects. As long as you have a compact object with an accretion disk around it, then you can potentially apply the same technique. So it's actually, the models are applicable to accreting neutron stars, stellar mass black holes, and supermassive black holes. Pretty much the same model, it works for all of them. I don't have time to show results for all these different scenarios. I will concentrate mostly in stellar mass black holes. They're my favorite sources for many reasons. And but if you have questions about the other ones, I'm happy to talk later. The spins of black holes are important for several reasons. As I say, they're a way to describe the black hole itself. In the case of supermassive black holes, I will only say that the distributions of spins with the mass of the black hole is very important to constrain observationally, because that will help us to distinguish between formation and evolutionary models for supermassive black holes. Whether, so a supermassive black hole, we're talking about millions to billions solar masses, so they're not formed by the collapse of a star. Therefore, they obviously acquire the mass through time by accretion. So there are questions about whether they grow steadily, accreting matter through the history, or they go through merger processes, and whether these mergers are hierarchical or chaotic. All these different scenarios will predict different sort of distributions for spins versus mass. So what I'm showing in the left here is a compilation, a recent compilation done by Chris Reynolds, showing the current state of our measurements for supermassive black holes. It's not very pretty, but it's the best we can do so far. And there are some some suggestions of some sort of distribution of having more faster black holes towards lower masses. In the case of stellar mass black holes, these are black holes that we observe pretty much in our galaxy. They're in binary system. They have a companion star, and they're accreting matter from that companion. They're easier to observe because they're much closer, so we can see them very bright in X-rays, and the measurements tend to be a little bit easier in that case. This is also taken from a review from Chris Reynolds, the current state of the spin measurements for about 22 sources that we have right now. There is no point in making a spin versus mass plot in this case. One, because we don't really know the masses very well for a lot of these objects. Two, because the masses are typically very close anyway. So they're all, we're talking about around 10 solar masses or so. But you see there is some sort of distribution. There is a large proportion of them. They're coming out with very high spins, close to maximum. This is the spin parameter goes, maximum is essentially 1 or 0.998. So there is a large fraction of them that wants to be a very high spin. There are two techniques here. One is the reflection technique I will be talking about today. Green ones are a different technique in which you fit for the continuum. If you have questions, ask me about it. But essentially what we see here is a good correspondence between the two techniques, except for maybe this one case right here. This is GRO J1655. I think it's interesting now that we're starting to get a lot of the spin results from gravitational wave events, the fact that they all seem to pretty much be closer around a particular value. This is the spin of the final black hole after the merger. So it gets a little bit tricky. It's not that easy to retrieve the individual spins of the two black holes prior to the merger, but there are several papers that suggest, or that they claim that these distributions suggest for most of them to be low spinning black holes. So this poses a bit of a problem for us in the sense that we see a lot of high spin sources, while like we're seeing essentially very low spin black holes. An easy argument is, well, they're different populations. They have different channels of formation. So you're seeing two different kind of black holes. They do. So the LIGO sources tend to be higher masses. That implies also low metallicity. So they are definitely different populations, but it also says something about, well, is it really all black holes are formed with very low spin? Then how all these guys acquiring their spin? Going from 0 to maximum spin takes a lot of matter to accrete, to gain angular momentum. So this comes with all other sort of problems that I personally find very interesting. So it motivates a lot of the work we're trying to do. So this is the cartoon picture of what we think Modres happens in accreting black holes. You have the black hole in the center. You have a lot of X-ray coming from the central region. Here is we depict a jet, which we see in the radio, but people also believe a lot of the non-thermal X-ray emission is coming from that jet or from the base of that jet. What is true is that we see in the observations, we do see this non-thermal emission, kind of like a power law with some higher energy cutoff dominating in most cases. And if this emission, part of this emission goes to the observer, of course, another part will shine the disk, it will be reprocessed. And this is what we call normally reflection. It's not real reflection, it's reprocess of higher energy photons into the relatively colder material of the disk. So that produces a richer spectrum with fluorescence lines, with some absorption features and many other things. If that reflection occurs then close to the black hole, it's going to get blurred and distorted because of all the gravitational effects that I mentioned. And it's very common that we see a combination of all these components in a single observation. So you need to fit for all of them. And this is an actual fit of a real observation of a real source, GX339-4, observed with NuSTAR and Swift XRT, covering a broad range in X-rays. Reflection is not a new business. It's been around for quite some time. I don't have time to go over the whole history, but earlier models, they just put a couple of lines for the ion emission, and they were concerned about modeling the Compton scattering inside the disk very well. Then people like Chris Reynolds start putting other elements because there is more than other than iron in this spectrum. But this was all neutral gas. This was all assuming everything is just neutral in coal. It was until Randy Rose and Andy Fabian start producing more realistic models in which you have to calculate the ionization balance within the material to understand, if the radiation is strong, you over ionize. If it is weak, you then actually see more neutral species. And what I've done since my PhD with Tim Kalman is improving on these models, working a lot on the atomic physics that goes into these models. Computers are better, so we can now make prettier plots in color, so that's also an advantage. Anyway, that's a silly joke. And as Mitch just mentioned, I realized while preparing this talk that yes, there is a very strong connection of all this science with Gila. Both Tim Kalman and Randy Ross were students of Dick McRae. They both went to continue this sort of work. And as Mitch said, Chris Reynolds, Jerome Bills, and maybe I'm forgetting somebody else. They're all been participants of this. All these models, of course, are motivated by observations. This is kind of like older generations of X-ray detectors. This is called RXTE. It was mostly a timing mission, so spectra wasn't necessarily the strong point. So the spectra are low resolution. With low, I mean about 1 kV at 6 kV, yet the features are broad enough and strong enough that you get to see them. Nowadays we have NuSTAR, as I mentioned. It's a much better resolution. It's essentially almost a factor of 10 better in resolution and sensitivity. So this is the same source observed with these two telescopes at different times, of course. And in the future, what we're hoping to see, we've been hoping for quite a while, is to get what is called microcalorimeters. These are the new generation of X-ray detectors that will bring the resolution even probably a factor of 10 even better. So we're going to be able to see in extreme detail what's going on in these sources. This is scary because I think every model is going to be wrong, but that means a lot of work for us. And because of this expectation of the new generation of X-ray instruments, we know we have to be ready. And to be ready means to have all the microphysics in the best way possible. So this is what we have done for quite some time. As I said, earlier models only consider maybe 2 or 3 transitions per ion of iron. What I'm showing here is the current database, atomic database that we have only for iron K, and we have hundreds of lines for the K alpha transition, a few more for the K beta transition, and this depends, of course, on the ionization state in which the material is. So this is all included already. It's not only iron, as I mentioned. There's a lot of work that atomic physicists that I've been involved with have put into computing iron and oxygen and pretty much any other species that are important in astrophysics. So there is a huge amount of work that I don't have time to talk about, but all this is important and is currently being included in our models. And this is the reason why when you include all this and you compute a high resolution spectrum, reflection spectrum with the resolution typical for a microcalorimeter, this is what you see. You see a really complex and rich spectrum of lines and many other features. Even from a theoretical point of view, it's hard to identify all these emission lines. It's not so trivial. And this was done 10 years ago already, because we thought 10 years ago that we were about to get a microcalorimeter flying, and we've been very unlucky. There is almost like a running joke now in X-ray astronomy with microcalorimeters. Apparently they have a curse. The first one blew up during launch. The second one had a problem, and the detector broke essentially. And the last one was Hitomi. It was a Japanese mission, took one observation, beautiful, and then there was a problem with the spacecraft and essentially just broke apart. So we're hoping for the next one to come soon. This is just unfair comparison with Randy Ross's earlier models. He wasn't able to do very high resolution. He had very limited atomic data, but this just to emphasize, the differences that we have in the current models now. And then we pack all this with, once you have the rest frame reflection computed carefully as we have done it, then you have to include all the relativistic effects. Once the photons leave the accretion disk, you have to understand how they affected in this perturbed space-time. This is done mostly by the group of Joran Wilms in Germany. Thomas Dowser is my main collaborator there, and he brought this together into a single model that we can provide a community to go and then analyze their data. And of course, these models depend on a series of different physical parameters that you hope to be able to measure. Then some of them, like black hole spin, I just mentioned, the inner edge of the accretion disk, but also you can measure the inclination, you can measure properties of the illumination and things like that. I'll talk in a minute. So what I want to talk now is several of the current observational. I say black hole binaries are my favorite ones because they essentially evolve in human time scales. A good analogy is like a volcano. Most of them, they stay dormant, they stay in quiescence, they don't emit much in X-rays, and every once in a while they just erupt. They go into an outburst, and that's what I'm showing here. This is just for a single source that is one of our favorites, GX339-4. It's a prototypical black hole binary because it does essentially everything we think they do, and it does it on a regular basis. So this is taken with the RXT telescope over 16 years of its lifetime. So this source went through several of these outbursts. And the good thing about that telescope is that it will, once an outburst was detected, it will essentially do a daily monitoring of the source. This is known as a harness intensity diagram, where you have in the x-axis is just the slope of the spectrum in X-rays, how hard or soft it is. And in the y-axis, you have X-ray luminosity. So you can see that the start of the outburst, the source becomes very bright, very fast. And on the right means that the spectrum is very hard. It means that it's dominated by a power law emission, the continuum. And we call that the hard state. And at some point, a certain luminosity, it just makes a quick transition to a spectrum that looks more like this spectrum. It has this softer thermal black body, multi-temperature black body kind of distribution that we believe is all emission coming from the accretion disk. So in one case, you have non-thermal emission that we think is coming from this coronal gas near the center. In the left, in the soft state where you have emission, is dominated by the disk, thermal emission. So we try to follow this with RXT. As I mentioned, RXT was not meant to do a spectroscopy, at least not in high resolution. It was a very poor resolution, but we figure there is so much data out there that there's something we might be able to do. So we defined these boxes in the higher state and combined data. This was already a few years ago. We combined all the observations within those boxes because they're happening a small amount. There is a small amount of time between those observations. So you get a way to combine all this data. And in fact, I showed this before. What you get is when you remove the continuum, you get very strong reflection features from all of them. There are 6 regions, meaning 6 different spectra, ranging in luminosity in the higher state. So we see clear emission from iron, relativistically broadened. This dip here is caused by the absorption of iron. The KH absorbs, and it's also distorted by relativistic effects. And the rest of it is caused by electron scattering in the disk atmosphere. So we fitted all these spectra with our models. It works very well. This is the kind of thing that I go and I put it in the fridge of my grandma, say, we succeeded. This is great. For you, it might not, if you don't do X-ray spectroscopy, it might not mean much, but this is actually very high signal to noise. This is 77 million counts in all this data that we're feeding successfully. So that tells a lot because it means that as any small discrepancy between the data and the model will blow up your chi-square and you will see like strong residuals. So the fact that we were able to achieve this fit is actually very, very telling. We measure the spin to be very high, we measure the inclination, we measure many other things. The interesting thing for me is that because there is so much data with this satellite, that we can follow evolution, which is actually more important, I think. And what we find is that we can measure the evolution of the inner radius. I said this sits at the ISCO, this innermost stable circular orbit. But at the beginning of the outburst, the disk doesn't have to be all the way there. That's just the closest you can see, but it actually, it seems to, the disk is forming, it's collapsing. We don't know for sure what happens, but from the observations, what it looks like if the disk inner radius is moving inwards as the source becomes more luminous in the higher state. And we were able to measure this. In this case, it's just a small range between maybe 5 RGs down to almost the ISCO, almost 1. This is, by the way, for a 10 solar mass black hole, that is roughly the mass of this one. This means that we're measuring a shift in the inner radius of 45 kilometers for a source that is 8 kiloparsecs away. So I always found that impressive. That's the power of X-ray spectroscopy. At the same time, we measure, if you can see a cutoff in the X-ray spectrum at high energies, it just, the power law doesn't go to infinity, it just dies at some point. And we believe that's connected to the temperature of the hot corona that produces the power law in the first place. And we see that temperature going down as the luminosity increases. So there is a connection. First of all, there seems to be a connection between disk and corona. Second of all, it makes sense that it becomes colder because you're getting more luminous. And in a hot plasma, that's pretty much what happens. You cool down by emitting a lot of photons. So we're able to track all these changes as they go away. What I'm showing here is now putting those results, which are shown in blue, with many other results in the literature for this source, all based on the same technique of reflection spectroscopy, down to luminosities. This is now in percent of the Eddington luminosity. So we're going down to 0.1% of Eddington. It's tricky to do measurements at low luminosities because the signal is low, and it looks like the emission is actually not so broadened because probably this is much farther away. So you lose those relativistic effects. So it's hard to make predictions or to make accurate estimates, but you see there are some limits, but the trend is clear. The trend says that the inner radius is moving inwards as the luminosity increases. We've recently been talking with Jason and Mitch and Nico about how this can be put in the context of their recent GRMHD simulations. And what they see is essentially something similar to the formation of an accretion disk as the luminosity increases to a certain point. So I think this is very roughly consistent with that picture, but at the very least, it shows the potential to start comparing complicated theoretical predictions like those from GRMHD with observational data. This is a different source called J1550 for sure. My postdoc, Riley Connors, worked on this one, trying to do a similar work to try to measure the spin and measure the inner radius. And we have this one observation in sort of the intermediate state. So when the source was going from hard to soft, but it became very, very luminous. It was beautiful data with very, very high signal to noise. We have, as you see here, a complicated collection of different instruments going from 1 kV all the way to above 100 kV. So this is pretty broadband for X-ray spectroscopy. And I'm not gonna bore you with the details of the fit. You have all the different lines here. These are different model components that were required. But in short, what it requires is disk emission. It requires reflection from farther away. So it gives you kind of like a narrow component of the line. It requires blur reflection, meaning reflection close to the black hole with all the relativistic distortion applied. The one interesting aspect of this source is that no matter what we did, we always came out with the same inclination for the reflector, for that part of the disk that causes reflection, about 40 degrees. The problem is, this is one source that has its properties very well measured, which is not common, and the inclination is supposed to be about 75 degrees. So usually when observers see this kind of situation, they will immediately say, well, you can have the disk to be misaligned. You can have the inner part of the disk to be misaligned with the orbit of the system. And there are theoretical arguments to make that happen. The problem in this case is a pretty large misalignment. 35 degrees is quite high, but it also is a problem, the fact that there is also very good constraints from the radio jet that suggest that the jet is aligned with the binary, with the orbit of the binary. So this will mean that you have an inner accretion disk that is misaligned with the orbit and with the jet at the same time. And that is, I found that very hard to believe. But that's where we are right now. One possible explanation that we're testing right now is the fact that all these models assume an accretion disk as a paper, is a razor thin disk. There's no vertical structure to it. And if this is indeed a high inclination source, you can imagine that any kind of vertical height from the disk will cause some obscuration of the central regions. And we have these are actually ray tracing simulations of that situation. And it shows that one of the things that happens is that you start killing the flux at the blue side of the iron line. And this is very important because that's a part of the line shape that gets modified by inclination. So in other words, what we could have is the case in which the source is actually a high inclination, the disk is completely aligned, but because of the obscuration, from the point of view of reflection, we see reflection as if will be produced at a lower inclination than what it actually is. So for that, we have to modify the models to include these sort of things, repeat the fit, and see if it works. We're on the process of that. But if it works, it will be quite interesting because it will be a way also to understand the vertical structure of the disk. Another really interesting result that came from the same source, coincidentally, it was when we look in the soft state. The soft state is, as I said, the state at which the source is dominated by thermal emission from the disk. So it doesn't look like a power law anymore. But yet, when you feed the continuum, you still see residuals that show signatures of reflection. So they show the iron line. However, they don't show what happens at high energies. That bump that I said, it was caused by electron scattering. That's called the quantum hump. And it's essentially just the high energy electrons in the power law being down scattered because of the interaction with electrons, right? So we don't get to see that. We see some small power law emission, but very weak. And none of the models will work well in this case. So almost for fun, what we did was to try a model that we developed for neutron stars. In the case of a neutron star emitting, instead of a power law, emits a black body, and that black body shines at this, it produces a reflection. And that actually works perfectly well to describe the data. So the way we interpreted this is that what we're actually seeing is returning radiation. So it's radiation, thermal radiation from the disk. Some of it goes to the observer, but part of that radiation will get bend around, will circle, will their path get distorted and goes back to the disk, shines into the disk, and that's what produces the reflection, not the power law component. The power law is not doing much there. And this is actually 40 years ago. Bingham predicted this in the 70s. And it's a big component. It could be 40% of the flux returning to the disk. So that's actually consistent with what we're seeing. So yet again, this is not, I wouldn't say a smoking gun, but it's very telling that something different is happening in the soft state. It could be connected to returning radiation, and we're putting that out into the models as well. Another interesting thing for me is to understand what happens in the material itself for reasons that they're mainly historical. All the reflection models have been produced at one single density, 10 to the 15. That's just a magic number. It kind of comes naturally for AGNs. This is how most of this business started with AGNs, and 10 to the 15 seems like a reasonable number. The reality is that especially in stellar mass black holes, those disks are expected to be in much higher densities. Any GRMHD simulation will tell you that. They can go to 10 to the 20, 10 to the 22, so several orders of magnitude higher. And so what we've done is now include this into the reflection models, just starting running models with higher density, and it actually has a pretty big effect. As you can see, Here, the different colors are densities going from 10 to the 15 to 10 to the 19. And there is a huge excess of energies caused just by density. Initially, we thought, or people before me, like Randy Ross, the argument was, all that matters is this number. This is called the ionization parameter, and it's the ratio of the flux to the density. And to zero order approximation is true. All that matters is what's the ratio to determine the shape of the spectrum, because you're essentially looking at the number of photoionizations over the number of recombinations that you can have. The problem is those are not the only two processes in these sort of scenarios. You have many other things, Compton, heating, cooling, you have Brent-Strahlung emission, and actually Brent-Strahlung, or also called free emission, turns out to be the main responsible for this excess, because it's that the rate for free emission scales quadratically with density, while many of the other rates scale, linearly. And I don't know what I did here. So the bottom line is density has turned out to be quite an important parameter, and it changes the way the spectral fits behave. Riley Connors, again, he was looking at a different source for U1630, and as just a consistency check, we try to predict what the ionization should be based on the luminosity and the distance of the source. If you have, if we observe this, we can estimate this flux by converting luminosity and doing ray tracing, assuming some sort of very idealized geometry, right? You idealize everything to be coming from a point source. This is called the lamppost model. And then you can tell with the ray tracing calculation how much flux is incident in the accretion disk. And if you take then the density coming up from the spectral fits, you can calculate the shaded region are the estimates for the ionization that should be in the gas. And again, ionization is yet another fit parameter in the model. So these are things that you're determining independently. So the red points are the fits, the values from the spectral fits, and the shaded region is what we're predicting with this simplistic way. And it's just a order of magnitude check to see that we are at least in the same ballpark. Interestingly enough, if you change the ISCO radius, or not the ISCO radius, sorry, the inner radius to 10 times ISCO, so you allow for a little bit of truncation, that consistency starts breaking very fast. So you're essentially receding the disk, so you cannot have the same sort of higher ionization that the spectral fits require. So this is a good consistency check we have done. And now more recently, as I mentioned at the beginning, we started including timing, the timing aspect into this model. And this is motivated by the fact that most of these sources, both AGNs and binaries, they can be very variable in time. This is a light curve, just a typical light curve of one of these sources. And you can see in very short time scales, there is tons of variability. If you think about, again, this simplified version of having a lamppost or all the emission coming from some particular point, you could imagine having the situation of that direct emission going to the observer, and the other part that goes in causes reflection takes a little bit more time, simply because it has to go to the disk, get reprocessed, and then go back. So we can measure that lag in time and make what is called a lag versus energy spectrum. And it has actually been discovered that this causes reverberation in the disk, and that reverberation has a shape very similar. It resembles the iron emission, it resembles the reflection spectrum. It's in a way, you're kind of seeing an echo in X-rays of the variability. So this was, first there was a tantalizing indication in GX339 with XMM data. Now there is a new instrument called NICER. It's mounted in the International Space Station, and it's specifically designed to do this beautifully. So Erin Kara published a paper in Nature for this new source, MAXI J1820, that became one of the brightest sources we've ever seen. Almost, it was like a gift to NICER, because NICER turned on and almost immediately this source came on. It was unknown to us. And you can see now much better these signatures of reverberation in the lag versus energy spectrum. The The way to do this, it becomes a lot more complicated because now you have 2 dimensions. Now you have to compute what is called the impulse response function. If you have a flash of light, you have to then understand how those photons propagate in the space-time. And you have energy on one side. This is kind of like what I've been showing, the spectrum. And but you also have time. So this all has to be encoded in the models now. The cool thing is that these sort of models now allow us to fit not only the flux spectra, not only the timing products, but everything together at the same time, simultaneously. So you have a strong, very, very high constraining power in these models. I warn you, things are getting a little more complicated now, so it's okay if you don't understand what I'm saying. I don't understand what I'm saying very much neither. I'll try to stick to the main points. The high density reflection that I mentioned a minute ago had turned out to be also important here because this is a lag versus energy spectrum, again, for the same source, MaxEJ 1820. It had this strong curvature at low energies. This is not flux, this is lag. The lag grows at low energies. This is the iron line. This is what people were already used to see. And model in simplistic ways, but modeling the lags at soft energies was difficult. And it turns out because this is mostly caused by reverberation, this is variability that we're seeing a high Fourier frequency, so fast variability. It all resembles the reflection at high densities that we're putting in these models. So we can actually fit this very well, only when we include the high density reflection. Another very interesting problem in the timing domain is the origin of hard lags at low frequencies now. So it's lower variability. You tend to see the hard photons lagging the soft photons. What this really means is that most likely something connected to the disk. So the part of the emission that comes at low energies is varying before and it causing variability in the hard photons. So this is hard to understand. You cannot explain this with reverberation. So the proposed model is that if you have fluctuations in the accretion rate that propagate through the disk, these fluctuations will cause fluctuations in the photons from the disk, emitted from the disk, they go to the corona and then produce variability in the corona. And that's why you see the variability first in the soft energies, the thermal part of the spectrum, and then later in the high energies in the non-thermal, kind of the power law part of the spectrum. In practice, what this causes is what we call the pivoting of the power law, what I'm trying to show here on the right, and this has been exaggerated just to show the effect, and it's because you're changing the seed photons that go into the corona, then they will produce changes in both the slope and the normalization of the power law. And this obviously is going to be followed by what happens to reflection then. Reflection is produced by that power law shining into the disk. So if you pivot the power law, the reflection pivots. This is what I'm saying. It gets complicated because now we have different sources of lags encoded into the model. You have the light crossing time, which is just a difference in time that takes photons to go from the corona to the disk. That's associated with reverberation. Then you have the lags caused by the pivoting of the power law, and then you have the lags caused by the pivoting of the reflection because of the pivoting of the power law. So all this is included into the model. This is again the same source. Now look at low frequencies. This is lag versus energy. Hopefully you see that it looks very different from what it looked before. And all the different lines are the different lags included in the model. The bottom line here is that in this case, the red one, which is the light crossing time, is negligible. This causes almost no lag. So the only way to explain this lag spectrum at low frequencies is by including this pivoting of the power law. So it dominates the signal. And then again, at high frequencies, when you go to higher frequencies, this is the same source observed at the same time. You just change the Fourier frequency to produce this lag spectrum. You go back to a lag spectrum that is dominated by reverberation more. Most of the lags are caused by this light crossing time. in a student of Erin Cannon at MIT, Jingyi Wang, who's part of this whole collaboration. She led a study very recently in the same source, and she looked at what happened when the source transitioned from the hard to the soft state. And by applying this model, as I said, we can fit everything simultaneously. So we have information about what happens to the corona. The high of the corona seems to have changed dramatically between, this is pretty much hard state on the left, going very high, hundreds of RGs towards the transition towards the soft state, meaning it looks like the corona is just expanding as the source transitions. The other curves, the plot is a little bit busy, but the red curve here is the flux in the radio. We see a steady jet in the hard state, and when the source makes the transition, this jet just gets quenched, it dies at some point, and this happens right at the same time that we see this big change in the coronal high, right? So the two things are connected. The spike at later times is a jet emission. It's like a blob that comes out later after the jet has turned off. At the same time, X-rays are going down. The hard X-rays are going down. So this all can be more or less, and I'm waving my hands a lot, which means I don't know what I'm talking about, but more or less can be explained as a corona that is expanding, but at the same time is just getting less efficient to produce that power law spectrum that we see. So I don't know how much time I've been talking. Probably I'm over my time, right? Yes, okay, so I'll pretty much stopping here. I just want to say, I start talking about reflection and how important it is for measuring spins. But where we are now is that we're having a huge amount of information. It has a tremendous diagnostic power to learn a whole other things about the systems, the structure, the geometry, what causes the illumination, etc. I have a couple of slides about the future. I'm not going to say much, just to say we keep looking at the plasma effects, very high densities. There are atomic effects that we're still not including. Things that are packed together very closely start feeling different atomic potentials, and this needs to be included in the models. And this is going to be very, very important for this microcalorimeter, the new detectors that we'll hopefully have very soon. And there is a polarization mission that is supposed to be launched later this year. And we're also thinking we have a program to include polarization in the reflection calculations as well. So I'll leave this just final thoughts. I think the future is going to be very bright for X-rays. There are many missions coming, and we're really trying hard to prepare our models to be at the same level of what the new observations are going to tell us. Thank you so much for your attention.
Thank you. So, question from the live audience?
So, are you very picture schematics about the thing of a black hole in line with the orbit of
Right.
So there's something that you like many examples, but
Yes. So reflection suggests 40 degrees inclination. The inclination of the binary orbit is being very well measured at 75 degrees. So as I said, typically people will talk about a disk that is misaligned, meaning the inner part of the disk is at one inclination, the outer part is aligned with the binary of the binary orbit, right? The expectation in that case is that that inner portion that is misaligned is at least aligned, so it's a misalignment of the angular momentum of the black hole. You expect the jet to be aligned with that angular momentum as well, but it turns out that the jet is aligned with the orbit. So that's a kind of a strange thing. And also the fact that it's 40 degrees versus 75 degrees, it pushes even those theoretical arguments of this misalignment to the extreme, I would say. No, we just measure the angle.
Apparently, it's not coming through well on Zoom.
Okay, so the question is regarding essentially this diagram that I'm showing It wasn't clear about the schematics and what was misaligned with what. So that's more or less the question. The second part of the question is whether we measure the orientation of the angular momentum, and we don't. We only measure the magnitude of the spin.
Keeping aside that difference, how much geometry?
How much, sorry, what?
Depends on the geometry of the
Okay, so the question is how much depends on the construction of the lamppost geometry that we have. It matters a lot because the lamppost is motivated by the fact that we see a particular illumination profile. We have a version of the model in which we don't assume any geometry, but we just assume that the emissivity of the disk follows a power law, and we fit for the index of that power law. When we do that, most of the sources come out with emissivity profiles that are very, very steep. And one way to explain that is with a very centrally located corona. So the lamppost, it just allows for that. It allows for a simplification of a very compact and centrally located corona. I don't know if that answers your question. Yeah. The question is whether we whether we expect the measurements of inner radius to depend on the lamppost. The answer is yes. To some degree, they do depend on that. In the extreme cases of very large or very small values, it doesn't. It depends more in the details, to a few percent, I would say.
It must have been an amazing talk because we don't have any.
Extremely clear then, yeah.
It's interesting result if you change the density of your reflecting atmosphere and have this huge soft just in X-ray words, this soft X-ray access.
Yeah, so that's
physically what is that? You said free, but
yes.
struggling to put it together.
So the question is a high densities that is I show that is excess in flux in the reflection, whether this is connected to the soft excess observed in AGNs. And we think it is. Before even doing these models, people have argued that the soft excess observed in AGNs was connected to reflection. Essentially, you have many lines, many atomic lines produced at those energies. Maybe I should say what the soft excess is when you look at many AGNs and you feed for the power law emission, the continuum, you get to see excess of flux at low energies, meaning around 1 kV or so. And it looks kind of very broad emission, featureless, most of it. The origin, the nature of this soft excess is still a matter of debate. It cannot be thermal emission because in AGNs, this will emit in the UV. So it's not very clear what it is. Some people talk about a warm corona, a corona that has low temperature and very high optical depth. I think that's a kind of oxymoron in physics. If it is a corona, it should be hot and optically thin. The other idea has been the reflection, blur reflection produces that excess. The high density makes the point even more strongly. Yes, we're fitting many different AGNs, and we're finding that they do prefer higher density than what we had before, but not as high as binaries. So it's in a way consistent with the picture.
Repeat the physical argument. What is that? Emissions is related to free.
In these models is mostly caused by free, the enhancement of free emission. Yes. From the atmosphere of the disk. Yes.
We've got one on the chat. Tom is asking, why does the distant reflection produce higher energy photons?
I'm not sure that is necessarily correct. Maybe let me see if I can. Do I need to repeat the question?
Why does the distant reflection produce higher energy photons?
Yes, I was asking whether I need to repeat the question for. Okay, all right. So I don't know if the question is because of this particular figure that I show. If it is related to this figure, the reason is the gravitational shift affects the entire reflection spectrum. So it will shift high energy photons to lower energies. But in general, there is nothing special about distant reflection producing higher energy photons. I hope that that's the case to answer the question.
If there are no other, one more question.
So, I see that there's a lot of evolution in the short time scale. But my question is, the Napoleon for the black hole in the mass, is that super slow or that we are going to see evolution on those scales?
Right, yes, and we don't expect, sorry, the question is whether parameters like the spin and the mass of the black hole are expected to change in the same time scales that we see all these changes occurring that I showed before. The answer is no. Those parameters are expected not to change in those time scales. They will take several million years to change. Yeah.
Great. There are no more further questions. Let's thank Javier once again.
Thank you so much. Yeah.